Hello and welcome to the Daily Space for today, Friday, December 18th, 2020. I am your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brains. And sometimes that science is just not as fulfilling as one might wish. In our top story, we have news of a missing supermassive black hole. Yes, folks, some of the largest objects in the universe can go missing. It is currently believed that all massive galaxies should have a black hole in their core that is proportional in size to the spheroid of the galaxy and the motions of its stars. While some small galaxies have been found without an obvious central supermassive black hole, massive galaxies have consistently had either obvious stellar motions or high energy emissions, or both, that are consistent with a massive object. This was at least true until folks started looking at the central galaxy in the cluster, Abell 2261. Now, once upon a time, we referred to these systems as CD galaxies, and it was believed they were an outcome of how clusters form. Today, they are more often referred to as giant elliptical galaxies and are thought more to be that first massive object that formed in the center of a dark matter halo in the early days of the universe. In this revised picture, these galaxies should be just like any other elliptical galaxy, just bigger and more likely to be actively merging with or consuming other systems. Astronomers, however, have been utterly unable to find high-energy X-ray light coming from this system. And the motions of the star clumps that can be resolved, they're not giving us definitive data that is needed either. In the radio, there is evidence of past emission, roughly 50 million years ago, but nothing indicating there's something there now. While it's entirely possible there is a supermassive black hole in the center of the galaxy, in the center of Abell 2261, that isn't consuming anything at all, and thus isn't giving off any X-ray emission. And while it's possible this galaxy doesn't have any close-in, fast-moving star clumps will be able to resolve, at least well enough to see orbital motions to detect a supermassive black hole. While it is entirely possible there is a supermassive black hole that none of these normal techniques allow us to detect, well, the fact that we can't detect it has folks looking for an alternative explanation. It's thought that this galaxy has undergone a recent merger, and dynamically, it is possible that the original supermassive black holes from each galaxy merged in such a way that they ended up rocketing off out of the system as gravitational waves were released in the opposite direction. There are aspects of this galaxy consistent with this story. The center of the galaxy has far more stars than is expected, and the densest part of the galaxy is 2,000 light years off center, which is extraordinary. If, and the data here is not at all definitive, if it turns out that supermassive black hole mergers can asymmetrically release gravitational waves and send the newly formed single supermassive black hole flying, then we should see more supermassive black hole missing galaxies. And we also have a cool new thing to look for in our gravitational wave data. Currently, detectors are only sensitive to smaller mergers, but the future has the potential to bring new systems sensitive to different kinds of events. We don't know exactly what's going on, and we can't know with our current technology. This is just an intriguing system. This is the kind of system that drives us to do science. The JWST may be able to reveal more details if it launches. But until then, we have a system with a secret. It may or may not have a central supermassive black hole. Either way, the solution is scientifically awesome. This research is described in a new paper accepted in the AAS journals and available on arXiv, with first author Kehan Glutkin.
Welcome back. Researchers are teaching computers to science more and more every year, it seems. Machine learning is the in field these days, and in new work coming from the Center for Astrophysics at Harvard, scientists have taught an AI to identify and classify supernovae. Using a dataset of 500 novae with spectra from the Pan-STARRS-1 Medium Deep Sky Survey, computers can now be used to find supernovae in observations that don't have spectra. And it turns out that there are a lot of observations without spectra. So by using this existing data set of actual observations and not just simulated data, the researchers created an AI that can identify supernovae with stunning accuracy. The Pan-STARRS-1 Medium Deep Sky Survey had 2,500 known supernovae in its catalog. And since only 500 of those had spectra, the data set could be used to train the AI to answer specific questions. Ido Berger, an astronomer at the CFA, explained, "The machine learning looks for a correlation with the original 500 spectroscopic labels. We ask it to compare the supernovae in different categories: color, rate of evolution or brightness. By feeding it real existing knowledge, it leads to the highest accuracy, between 80 and 90%. This technique is going to prove even more useful once the Vera Rubin Observatory is online, because while the Large Synaptic Survey Telescope will surely discover a ton of new supernovae, the percentage we'll have spectra for will not increase. Now scientists will be able to use all the other components of the observations to classify all those new novae we find." The corresponding papers for this work are published in the Astrophysical Journal.
High energy events like supermassive black hole mergers and some supernovae and the mergers of neutron stars all have the potential to give off massive amounts of energy via gravitational waves, while also sending out particles and light across many wavelengths. This triple feature of particles, light, and gravitational waves turns astronomy into a multi-messenger field where we can start to look at things through a variety of instruments that probe radically different kinds of physics. This is all really new, and folks are still exploring all the ways they can leverage the combined information to understand our universe. In a new paper in Science with lead author Tim Dietrich, a team of astronomers examine how merging neutron stars may be usable as standard candles and what we can learn about the interiors of these weird stars from so many forms of data. So far, their estimates of neutron star sizes are in line with prior estimates made using pulsar data, and the error bars are such that it's not yet possible to determine if neutron stars are solid neutrons all the way through, or if their core is some denser, weirder substance that would allow neutron stars to have a smaller radius. It's good to see consistency, and we can only hope to see the error bars coming down over time. This team also found, again with fairly hefty error bars, that the strength of detected gravitational waves can be combined with theoretical calculations about the initial energy in the waves to sort out where the neutron star mergers were located. Essentially, if we know how much energy the wave should have contained at its origin, and we can measure how much energy it does have as it passes through the Earth, we can calculate the distance. By combining thus calculated distances with measured redshifts, that recessional speed of the galaxies containing the neutron stars, we can calculate how fast the universe is expanding. Preliminary results with error bars yield a value of 66 kilometers per second per megaparsec. This means every megaparsec chunk of universe is all other techniques. Well, it's for the cosmic microwave background related cosmic expansion. And techniques and infrastructure are techniques matching old results. And I can't wait to see how multi-messenger astronomy expands our understanding of the universe.
Did you know that there is a cosmological lithium problem? I did not. But a team led by scientists at University of North Carolina at Chapel Hill did, and they may have taken the first steps to solving this problem in new work published in the journal Science. We use lithium for a host of important purposes, from powering cell phones to creating medicine. And we are pretty certain that much of the lithium in our universe was created during the Big Bang. But we haven't been able to measure that lithium anywhere in the stars, and that is the problem. Enter this team of who took spectra again of two very old white dwarfs and found the crushed up remains of what are likely large asteroids. From the spectra, the team was able to determine the composition of those former rocky bodies, and they managed to measure both lithium and potassium for the first time. J. Christopher Clemens, the designer of this new spectrograph, explained the importance of the discovery. Our measurement of lithium from a rocky body in another solar system lays the foundation for a more reliable method of tracking the amount of lithium in our galaxy over time. And lead author Ben Kaiser noted, eventually, with enough of these white dwarfs that had asteroids fall on them, we will be able to test the prediction of the amount of lithium formed in the Big Bang. It's always a good day in science when we have a breakthrough on a long-standing problem. So hats off to this team and their amazing work.
In what's becoming a recurring theme, we have a news story on how scientists thought something must act one of two ways. And the reality, once again, is both things can happen. In this particular case, we're looking at volcanoes. Trying to understand what exactly a volcano is likely to do has been of long interest, but so far just hasn't been all that possible. This is because volcanoes are complex systems that combine vast networks of reservoirs and tubes that store and transfer magma from deep in the earth to the surface above. Understanding how these networks are made is all the more challenging because they are located underground. And even the most sensitive ground-penetrating radars don't give us the kinds of resolution needed to completely understand exactly how magma pushes its way through rock. Luckily, erosion and plate tectonics can help. There are various places on our planet where the guts of volcanoes have been exposed in cliff faces and volcanic fields. In order to build a new and better understanding of volcanoes, an 85-person workshop was convened in Argentina that combined 2 days of scientific meetings and a 3-day field workshop that looked at rock formations altered through magma intrusions and other volcanic features. Of interest was how rocks deform when magma encounters them. Specifically, are they cut like with a knife or are they pushed like with a probe? In the knife scenario, magma cuts into a rock that then tears and splits out of the way. In the probe scenario, the encountered rock compresses and deforms as it is pushed along. It turns out that both these situations happen. Sometimes magma cuts through rock and sometimes it pushes. And this has consequences for how we model volcanoes and what we look for. Put simply, there's no one way that volcanoes store and transfer magma. And when we see the ground begin to bulge, all we can know is something is moving, and not if that something is gearing up to come out through the surface. These are not satisfying answers. This does not help say when or for how long a volcano may erupt. But this does tell us we need to model things in more ways than one, and that our predictions need to say, if this, then we see that, and if this other thing, then, well, something different is going to happen. We need to have predictions that have two possible outcomes. Our planet is complex, and the data looked at in this research is also complex. The report from this research conference has now been published on EOS and includes numerous references to individual papers that discuss different aspects of this work in detail. The data analyzed wasn't just confined to the field studies they did looking at outcrops in Argentina. They also were able to analyze data that, well, is standardly gathered by academics along the lines of gather what your grant allows. This academic data can then be, well, combined in this case with data obtained with more expensive equipment and larger data gathering budgets by petroleum companies. This is awesome. With this additional information, researchers were able to apply their theoretical knowledge to gain new insights that are leading to new laboratory experiments to try and model what's going on at a much smaller scale. I can only hope that we see more of these joining of industry and academia ventures in the future.
I seem to be talking a lot about dust this week. It's an important issue in a lot of our planetary science research. However, we mostly look at dust and its physical effects, like erosion, or air quality, or glacial stability. And now it turns out that we may be overlooking a very important effect, an electrical effect. According to new research from Washington University in St. Louis and published in Journal of Geophysical Research Planets, electrical effects can affect the chemical composition of a planetary body's structure and atmosphere in a relatively short time. The study focused on amorphous sulfur and chlorine salts found by the Curiosity rover at Gale Crater on Mars. And per the press release, the chemical signature of these materials could have been induced by electrochemical processes during Martian dust activities in a relatively short geologic time frame, years to hundreds of years. These electrochemical processes could cause changes in the crystal structure of minerals, removing water and causing the oxidation of sulfur, chlorine, and iron. This research should be used to make further decisions about our research priorities in upcoming Mars rover missions, and it suggested that we look to the subsurface of the red planet, where we could find ancient materials that might even have evidence of biomarkers. And I'm all for that. And finally, because it's that time of year, the European Space Agency has provided us with a seasonal image of Mars, an angel, and a heart. These formations were spotted by the ESA's Mars Express near Mars's south pole in November. On a less whimsical note, the red in these images is caused by the composition of the sand dunes, namely sands that have a lot of dark rock-forming minerals such as pyroxene and olivine. And since it's summer on Mars, the amount of polar ice is at its lowest, revealing all that gorgeous dark red sand. There's even more cool science involved here. The angel's hand may be a sublimation pit where the ice has undergone rapid sublimation and left a divot in the surface. The halo and head are an impact crater. And while the formation of the heart is something of a mystery, scientists think it may have existed deeper below the surface in layers of material formed by ancient volcanic activity and been revealed by erosion over time. Also really interesting is the dark patch of crisscrossed lines off to the left side of the image. Those are made by dust devils on Mars. So we have something for everyone in this image: love, hope, and a little devilish work. Happy holidays, everyone.
Beth and I are working to find new segments to bring you new information about astronomy as we expand out our show. One of the things we're looking to do is spend time on Fridays going over things you can explore, get, enjoy that are perhaps more of a tangible nature. As we start, well, it's not so much a tangible nature, but we want to let you know about other podcasts that are out there that you can learn more astronomy from. Some of them even come from us. So, for instance, today, later on in the afternoon, we will be recording Astronomy Cast right here on CosmoQuest X on twitch.tv. This show is now a teenager. We have almost 600 episodes, and this is something that Fraser Kane and I do as a labor of love that each week explores a new topic in depth, discussing not just what we know about our universe, but how we know what we know about our universe. So come check it out. But this isn't all we have to offer. We also put together the 365 Days of Astronomy podcast, which is really an anthology that brings together a myriad of voices from all around the world. First launched in 2009, the 365 Days of Astronomy podcast was meant to be a one-year experiment during the International Year of Astronomy that allowed people to, well, learn more and see just how many different people contribute in how many different ways and are sharing their passions through audio. Well, it's no longer 2009, but this show continues on every day. And you can subscribe to it on iTunes, Google Play, or wherever podcasts can be found. This includes Spotify. Beyond that, we work with so many different people. Fraser Kane has his guide to space. Paul Matt Sutter does space radio and so much more. Go out, explore, and Beth's not going to brag about it, but she does this little YouTube series called The Grudge Report that looks at the science in, well, one of my favorite new shows, Star Trek Discovery. So go out, listen to some science, and enjoy. This has been The Daily Space.